Hello, my name is Duke Pauli, and I'm assistant professor in the School of Plant Sciences here at the University of Arizona. My lab works on heat and drought stress tolerance in crop plants, and we use a variety of tools to research this, from phenomics, quantitative genetics, and modeling. Before I begin, I'd just like to quickly thank the organizers of the meeting for giving us the chance to present our work here. We're really appreciative of that. So today I'd like to share with you the stuff that we've been doing on large-scale data phenomics processing. I think this is a problem that's becoming more prevalent in plant science. Basically, as phenomics takes over, we're generating larger and larger data sets. And specifically, I would like to share how we are trying to leverage high-performance computing and new tools like virtual reality to explore and understand phenomics data. So as we know, over the last decade, phenomics has really become of age. And basically, proximal sensing is generating these large multimodal data sets, and it's becoming easier and easier as the technology gets better and better. This has led to the creation of a new bottleneck, and I would argue that is data processing itself. So my research group, we've had to confront this problem largely head on at a pretty significant scale. The University of Arizona is home to the UA Field Scanner. This is the world's largest outdoor robotic phenotyping system that we're aware of. The scanner covers an area of 2 acres, just under 1 hectare, and it operates continuously around the clock, as well as across the growing season, allowing us to capture temporal dynamics of crop growth in response to environmental conditions. Some of the sensors that are carried by the scanner and the amount of data that they generate include an RGB camera that generates about 550 gigs of image data, which is about 16,000 images. A thermal camera capturing about 5.5 gigs of image data. A fluorescence camera that generates about 80 gigs of data. A 3D laser line scanner, which is similar to a LiDAR, that generates about 300 gigs of data per scan. And we have 2 hyperspectral cameras covering 400 to 2,500 nanometers that generate approximately 600 gigs of data. So on a daily basis of routine scanning, we generate about 1.5 terabytes of data during the day. Our max collection capacity is about 10 terabytes. And so as you can see, these data volumes quickly surpass what most computational processing systems can handle. And so for our group, we needed to come up with a way to process these data in a timely fashion so that we can do QC on them in case we need to make adjustments to the scanning protocol, as well as just to basically get the data in the hands of our collaborators. And because of this, we found that existing pipelines, and there are not that many out there, really couldn't handle the volume of data. So given our needs, we developed PhytoOracle, an open source, scalable, modular workflow. By open source, I mean that all the code and documentation files are open access, and we have several tutorials on how to use the pipeline. Additionally, we make all of our raw and processed data available to the public through Cybers. By scalable, we mean that PhytoOracle uses distributed computing to leverage computational resources like high-performance computing platforms, or even smaller networks to distribute the work among resources that are available. PhytoOracle is modular because the various processing steps and trait extractors are containerized using the software Singularity. This means that you can customize the pipeline for your data and needs by selecting the function or trait extractors of interest. We basically wanted to design this like an app store so that you can plug and play and use the different components of the pipeline to meet your own needs. The pipeline uses Makeflow and WorkQueue to schedule, organize, distribute, and compile results to a manager node, and then to communicate with the worker nodes where the actual computations are performed. The biggest point I want to highlight is that PhytoOracle works with various data, not just our scanner data. Our group and other labs use it to process drone data, which it does really well, but it can also process something like tractor and cart data too. On this slide, this is just a quick example of how we use the pipeline to process image data. So basically, we're taking the generated orthomosaic, identifying each individual plant across the field using RCNNs. In this case, we're identifying about 30,000 plants. We do this for all scan dates across the season and then employ agglomerative clustering to make sure that we're associating each individual data point with the same respective plant in the field across all scan dates in the season. This allows us to compute and extract phenotypes for each individual plant for each individual scan. And because of this, we can build really exceptionally large databases of our field that capture all the trait data across time and in the season. And so to give you an example of how we're doing this is here's the trial that we're looking at. This is a lettuce diversity panel grown in 2020. You can quickly see there's a ton of phenotypic variation within lettuce. And so what we wanted to do to kind of better explore this was to see if we could get this in a virtual reality environment. So here's a demonstration that we've put together. This is a reduced representation of the lettuce field I just showed you. It's a smaller scale just for the purposes of making a demonstration video that's reasonably fast. As you can imagine, as you add more plants and add more data streams, it can get a little bit slow. So in this instance, we have a handheld field book. You're walking through the field. You can select the plant of interest. When you do that, it pulls up all the associated data that has been processed and stored in our database. So in this case, you can look at the growth curve for this individual plant over the season. You can look at the collected thermal data. And then finally, you can look at the individual plant segmented out of the original scan. And this way you can investigate and look at the plant more closely. So as you walk through the field, you can quickly select other plants, pull up the same types of data. So we recognize at this point it's kind of just like a gee whiz tool. But I think as we build on this and add more utility to it, it becomes a very nice native environment for which people can explore the field. Specifically for ourselves, it's a great tool because it allows our collaborators to come to the field and use their domain knowledge to look at the data. And this is really helpful because I can't show everybody our lettuce field, but if you can put on a set of goggles and make the trip, it's much easier. And so this allows us to basically interact with and provide data to other people, allow them to use their knowledge to investigate the data, and basically leverage it to the fullest extent possible. So quickly, here are just some of the resources in terms of the documentation, containers, the workflows, and data for PhytoOracle, and where you can access these. And I'd like to close by thanking the group, specifically my lab and Eric Lyons' lab here at the University of Arizona, as well as our collaborators at Danforth and funding from DOE. With that, I thank you for your time. If there be questions, I'd be happy to take them by email. And again, I would just like to thank the event organizers for having us.